Did you know that the oxygen we breathe could depend on processes hidden under the ocean? Researchers at Yale University and other institutions have proposed that terrestrial tectonics played a crucial role in eliminating materials that consumed oxygen. This means that the air we breathe today could depend on geological processes that have been operating for billions of years. The Earth did not always have an oxygen-rich atmosphere. For much of its early history, oxygen was almost non-existent. The first photosynthetic bacteria appeared long before oxygen began to accumulate in the atmosphere. The Great Oxidation Event, which took place approximately 2.4 billion years ago, marked a significant increase in oxygen, but the atmosphere continued to oscillate in its concentration. The key question was never who produced oxygen, but why it did not accumulate. Researchers have found that organic carbon and minerals like pyrite reacted with oxygen, eliminating it before it could accumulate. The new study suggests that the key was to remove these chemical consumers from the surface. Under the oceans, tectonic plates move and collide, resulting in a process called subduction. This process drags materials into the Earth's mantle over millions of years, affecting the chemistry of the atmosphere. The cold subduction, in particular, allowed the planet to hide some of the main enemies of atmospheric oxygen. This geological mechanism has been fundamental to the conservation of oxygen in the atmosphere. For oxygen to increase, it was necessary for certain materials that consumed it to disappear from the surface circuit. Tectonics evolved into colder subduction systems, allowing the Earth's interior to hijack reducing compounds. This finding does not eliminate the role of photosynthesis, but changes the focus of the problem. Attention is shifted towards the mechanisms that prevented the conservation of oxygen, rather than focusing solely on its production. The authors of the study have compared the evolution of subduction with episodes of oxygenation in the history of the Earth. The results show a remarkable coincidence between these events and the phases of planetary oxygenation. Research also suggests that the internal dynamics of a planet can influence the amount of oxygen that remains in the atmosphere. This complicates the search for life in exoplanets, as two similar planets could have very different atmospheres.